So yesterday we started 6.1, didn't quite get through the first part, so we'll finish that up, probably take about 25 minutes to finish that, and then we'll do the last part of 6.1, which was part 2. Okay, and that also will probably take about another 30 or 35 minutes, so you should be able to get through everything. So radians are another way to measure an angle, right, besides degrees. So the first thing I'm going to do is just show you a picture, kind of give you a visual for what a radian is. Okay, so what I've drawn here is a circle, and I've put an angle with its vertex right at the center of the circle. And the angle has two rays, ray CA and CB. Well, CA hits the edge of the circle right here. CB hits the edge of the circle right there. If you connect A to B, okay, following the path of the circle, you create what's known as an arc. Okay, that's arc AB, okay, in red. Arcs are not directional, so you could also call it arc BA. And that's the symbol for it, arc AB. Now, if you go back and just look at the word radians, does that look like any other word that has something to do with a circle? Chris?
Radius.
Radius. Okay, and the way I'm going to describe to you what a radian is going to use the radius. So, let's say that we measured the radius in this circle from point C to B or C to A. It should come out the same. We measured the radius in this circle and we get a number. Then let's say we took a piece of string and we measured the length of that arc by putting a piece of string on it and then bringing it over and then straightening it out like on a ruler. If the length of that arc in red and the length of the radius in that circle came out to be the same, then you would have a picture of exactly 1 radian. So angle ACB would be exactly 1 radian if the length of the arc in red is exactly the same as the length of the radius. If the length of the arc is bigger than the radius, then you would have an angle here that's bigger than 1 radian. If the length of that arc was smaller than the radius, you'd have an angle here that's smaller than 1 radian. Okay, but if you move that terminal side just right, so that the length of the arc matches the length of the radius, that's exactly an angle of 1 radian. It doesn't help us to convert between degrees and radians, but it kind of gives you something you could visualize to see what a radian would look like. Okay, in this case, I think the terminal side is a little bit too big. I think that arc is a little bit longer than the radius in that case, so we probably have to bring it in just a little bit. But any question on that idea? Okay. So now what we want to think about is something a little more numerical. How do we actually change between the two units that we measure angles at? How do we get from radians to degrees or the other way around? Well, in order to convert between any two things, all we have to know is kind of something we can start with. Right? Some fact that we know is true that we can start out with. All right, so I'm going to give you guys something to start with. Okay, we can't prove everything, but we got to start with something. So the fact I'm going to give you is going to have something to do with a circle. Okay, and this is going to help you to convert between radians and degrees. Now, this isn't just any circle. This is specifically a unit circle. We're going to study more about unit circles later on. But for now, all you have to know is a unit circle is just a circle with a radius of 1. That's all. Okay, so it's a certain size circle. And there's something special that happens on a unit circle when you draw an angle. And I'm going to show you what it is. So I can scroll back up. We'll come back up to that diagram if you still need it, but I just want to scroll down to this. This is what happens on a unit circle. If you draw an angle on a unit circle, and you measure the angle you just drew in radians, it will come out exactly the same as the length of the arc. So in a unit circle, if you draw an angle and then take a measurement of it in radians, it will come out exactly the same as the length of the arc. Okay, so how does that help us? Let's go back up. So the measure of the angle is equal to the length of the arc. So if I drew an angle here that was, I'll just make an angle like this. Let's say that angle was 2 radians. Then this arc would be 2. If that angle was 3 radians, this arc would be 3. The size of the angle and the size of the arc will always match on this type of circle. Any question on that? So, let's say I had something like that. That's a quarter of the circle, right? That's a 90-degree angle. Whatever that angle would be in radians, because we don't know what 90 is in radians, right now. It equals some amount of radians. But the way we could figure out how many radians it is the size of this angle is equal to something else that we already know how to find. The size of the angle is equal to the length of the arc. So how would you figure out the length of that arc? Yeah?
Convert the degrees to radians?
We don't know how to convert degrees to radians yet. That's what we're figuring out. But this angle is a 90-degree angle, and I'm curious how big that angle is in radians. I know that the measure of the angle is equal to the length of the arc. So if I can find the length of this arc, then I'll know the measure of that angle in radians. But how would I get the length of that arc? Well, what is that arc? It's part of the what? Yeah?
Part of the circle?
What about the circle? The circle's
shape?
Yeah, I'm thinking of something more mathematical word. Yep.
The circumference?
It's part of the circumference. Can you tell me exactly what part of the circumference? What part of the circumference is that arc? Yeah.
It's a quarter of the circumference.
It's a quarter of the circumference. So, as long as we know how to find the circumference of that circle, we could take a quarter of it, and that would be how big that angle is. Because the size of this angle in radians is going to be exactly the same as the length of this arc. So you'd have to find the circumference, then we could divide it by 4. Well, what if I wanted to know, let's say this, 360 degrees. Okay, so now instead of 90, the terminal side is going to get rotated all the way around. And the terminal side is going to be right back on top of the initial side. That's a 360-degree angle. Look at the arc that I just drew in red. How much of the circumference is that arc? Yep.
All of it?
All of it. So instead of even thinking about a quarter of a circumference, let's just think about the whole thing, because that's going to be an easier formula. This is 360 degrees. Goes all the way around the circle. I'm going to try to find the length of this arc that goes all the way around the circle. We call that the circumference. If I can find the length of that arc that goes all the way around the circle, it will be equal to the measure of the angle. So all I have to do is find the length of the arc that goes all the way around, and that'll tell you how many radians to go all the way around. So what's my formula for the circumference of a circle? Yep.
2 pi r.
2 pi r. And we are working with a circle that specifically has a radius of what? Francesca? 1. 2 pi times 1. How much is 2 pi times 1? Yeah.
2 pi.
2 pi. So the length of this arc in red that I just drew is 2 pi. What is the length of the arc equal to? It's also equal to the what?
2 pi.
The what?
Would it be 2 pi?
So, well, yes, the length of the arc is 2 pi, but the length of the arc is also equal to, yeah?
360.
Yes, it's equal to the 360 degrees. It's equal to the angle. The length of the arc is equal to the measure of the angle. So now, in radians. So now we know the measure of the angle to go all the way around a circle is the same as the circumference of the circle, which is 2 pi. So now we know 360 degrees equals 2 pi radians. So let's write that down right here. Well, actually, I wrote it up here. 360 degrees equals 2 pi radians, which is also equal to 1 revolution. 1 revolution is 360 degrees. So that's a fact that's always true. That's like saying in 12 inches, there's 1 foot. That never changes. There's always 2 pi radians in 360 degrees. All right. Now, that conversion is okay, but we can simplify it a little bit. We can make the numbers smaller. Does anybody see what I could do on both sides? As long as you do the same thing on both sides with division, it's still true, maybe just a little bit easier. Yeah?
Divide by 2.
You could divide each side by 2. So if 360 degrees is 2 pi, 180 degrees is 1 pi. That's better, but even that's kind of a weird way to give someone a conversion. When you tell someone a conversion, you usually tell them a certain number in the conversion, and it makes it easy for them to do. What number is usually in every conversion that you would tell someone? Yeah.
1.
1. Always use a 1. Right? If you're going to tell somebody how many minutes in an hour, you would say there's 60 minutes in an hour. 60 minutes in 1 hour. You wouldn't tell them that there's 240 minutes in 4 hours. I mean, you could, but you're making it more complicated. Right? 60 minutes in 1 hour. So let's do the same thing here. Let's get a 1 on one side of this equation. Depending which side we get a 1 on, is going to help us to convert either from degrees to radians or radians to degrees. Let's get a 1 on the right side. What would I have to divide both sides by to get a 1 on the right? Yeah, okay.
180.
180 degrees. So let's divide by 180, divide by 180, and let's write down what we have, and I want you to maybe see a pattern. Pi over 180 radians, bless you, equals 1 degree. So now I have a formula for 1 degree. That's what 1 degree, so you could type that in on the calculator and see what it is. Now, what if I wanted a formula for 2 degrees? Using this equation, what could I do on each side, and it would give me a formula for 2 degrees equals something. Think about something we could do to both sides, because that equation is true, right? Everyone agrees that's true. So as long as we do the same thing on both sides, it's still true. But I just want to have a formula that says 2 degrees equals. So think about what you could do to the right to make it a 2, with multiplication. But if you do that on the right, you have to do it on the left. Yep.
First be multiplying the 2.
You can just multiply by 2. I'm going to erase this in a second. I just want you to look at a pattern. You could multiply by 2, and you could multiply by 2. Now you have a formula to convert 2 degrees to radians. What if I wanted a formula to convert 5 degrees to radians? What could I do here? Yeah?
Multiply by 5.
You can multiply both sides by 5. It's not important what you put in the black box. What's important is this part. If you want to convert degrees to radians, you take whatever you're trying to convert and you multiply it by pi and you divide it by 180. That's the general pattern. To convert from a degree to a radian, step 1, multiply by pi. Step 2, divide by 180. Those are always the 2 steps to change from degrees to radians. Okay, so that gets us one way. Now we want to finish up with how do we do it the other way. So let's go back to that equation we had in black again. Pi radians equals 180 degrees. And now let's get a 1 on the left side. What could I do on both sides of this equation to get a 1 on the left? Yeah.
Divide by pi on both sides.
Divide by pi. And again, we're going to look for a pattern that kind of comes up here. Okay, pi divided by pi is 1. Now you've got a formula for 1 radian. So if you wanted to know what 1 radian is, you could type that in. It's 180 divided by 3.14. I think it's about 57, roughly. Now, let's do the same thing. What if I wanted to know how much 2 radians is? What could I do to both sides of that equation to get a formula for 2 radians? Yeah?
Multiply each side by 2.
Multiply each side by 2 times 2. If I wanted a formula for 7.5 radians, I could multiply the left side by 7.5, and it would be 7.5, and then I could multiply the right side by 7.5. Again, not important what you put in this red box. What is important is whatever's in that box. If you want to change from a radian to a degree, multiply by 180 and divide by pi. Those are the 2 steps to change from radians to degrees. Multiply by 180, divide by pi. I have the 2 steps written just like we did a second ago. So now it can get a little confusing. One's multiply by 180, one's divide by 180. They're very similar. So I'm going to give you a way that you can remember without even really having to memorize this. You just have to remember 2 things. when I say degrees, the number I want you to always think of with degrees is 180. Degrees, think 180. Degrees, think 180. When I say radians, I want you to think pi. So that's the number I want you to connect with radians. Pi, radians. Pi goes with radians. 180 goes with degrees. If you can remember those two things, this will all be automatic. All right, so now let's practice changing between degrees and radians. All right, so when you convert, you only have two options. It's either going to be the pi over the 180, or it's going to be the 180 over the pi. Think about 30 as a fraction. The goal here is to get rid of this degree symbol and end up with radians. You have a degree symbol in the top. Where would the degree symbol have to go in this fraction to cancel it out in this fraction? Top or bottom? Tyler?
The bottom.
It'd have to go in the bottom. If the degrees are in the bottom, that means the radians are going to be in the top. When you see radians, what number did I always say to think of? Yep. Pi. And when you see degrees, what number do you think of? Yep. 180. And if you look back at the notes we just wrote, that's how you convert degrees to radians. Multiply by pi, divide by 180. But I didn't have to memorize that. All I had to do was think about how to cancel out the degree symbol, and it'll put it in the right spot automatic. That's gone. And then we reduce what else we can. 30 goes into itself once. How many times does 30 go into 180? 6. So your final answer here is 1 times pi divided by 1 times 6. That's how you write the final answer. Is there anything, when you look at that, is there anything you think that I might have forgotten, but I didn't? Or you think some people might think I forgot to put? Yeah?
Maybe the degree symbol?
Well, is that a degree though? No. Well, you convert it to radians, so the degree symbol's gone. So hopefully you wouldn't think that we need the degree symbol, because that's gone. But what else would you think that maybe I forgot, but I didn't? Yep.
The radian.
Yeah, the RAD. You have to get used to not seeing RAD. I just wrote it this first time just to kind of help you, but you never write RAD after a radian angle. So how do you know if it's radians? Well, we only have 2 units that we use to measure angles. We have radians and we have degrees. If it's degrees, you'll see the little circle. If you don't have the little circle, it's radians. If we had 15 different units, then that would be a problem. We'd have to label each one of them, but we only have 2. So it's easy. A label, radians. If it has a label, degrees. And a lot of times, angles that are multiples of 30 or 45, they will leave them as an exact answer. They won't do pi divided by 6 on the calculator. If they want you to, they'll write it out. They'll say round to 2 decimal places. Let's try another one. 45 degrees. Okay. Matt, where's degrees going to go to cancel it out in this one?
The degrees?
Yep.
Bottom.
Bottom. And what number always goes with degrees?
180.
And that means the number in the top will be?
Pi.
Pi. Degrees is gone. Again, RAD is right there. It's invisible. Just pretend like it's there. And 45 does go into 180 evenly. How many times? Jack? 4. That's a 1. That's a 4. Final answer here will be, Eli, what will it be?
Pi over 4.
Pi over 4. That's it. All right, let's try, let's see if we can do this one quick. We know 30 is pi over 6. How does 60 compare to 30?
Double.
It's double. So if you know what 30 is, all you have to do is take what you already have and double it. There you go. So once you start to memorize some of these angles, like if you said to me, well, what's 120? I would just say in my head, okay, I know 30. 30 is pi over 6. This is 30 quadrupled. So just take pi over 6 and multiply it by 4. Okay. If you ever forget, you can always go back to converting it from scratch. Multiply by pi, divide by 180. But some of these are going to become automatic soon. Let's try this one. We know 30. How does 90 compare to 30? Tyler?
3 times.
It's triple. What did we get when we converted 30? Yep.
Pi over 6.
We got pi over 6. That's 30. If you triple it, that's 90. Without going back and converting it from scratch. And what would 3 pi over 6 reduce to? Yep.
Pi over 2.
Pi over 2. And hopefully some of it's starting to click a little bit, because if you go back and look at what we had, we know that 180 is pi. Well, we just wrote pi over 2. We wrote half of that. So 90 is pi over 2. Half of 180, you divide each side by 2. All right, let's try this way. Convert to degrees. Now again, just pretend that you see RAD written right there. You're not going to see it, but RAD is in the top. So how about Zach? Where's radians going to go to cancel out in this one? Yeah, radians is going to go in the bottom. And Ashley, that means degrees is going to go where?
On top.
On the top. Again, I don't want you to have to write that. We got to get used to not seeing it. So radians is in the bottom. Radians is in the top. Cancels out. If you want me to write it the first time, I will. But you got to get used to not writing that. What number do we always put with degrees? Dave? 180. And the number that we always put with radians is
Pi.
pi. So you can see it's the conversion we did last time flipped. What else cancels out here? Not even reduces, it cancels out completely. Pi. Pi. And now there is something that reduces. How many times does 2 go into 180? Francesca?
90.
90. So I'm left with 3 times 90 with a degree symbol. And that's my answer. Now if I wrote that, is that right? No, that's 270 radians. You forgot the degree symbol. So you do have to put the degree symbol when it's a degree. Any questions on that? All right, let's try, I think these are pretty similar. Let's do this one. 2 pi over 3. Same directions, convert to degrees. All right, when we want to convert to degrees, Jake, what number goes in the top?
180 degrees.
180, just like last time. Francesca, do you have your pass or 180 degrees? And Sarah, what number goes in the bottom?
Pi.
Pi. RAD, RAD cancels out. Pi, pi cancels out. What else can I do? Yeah.
3 and 180 reduced. So it's 1 and then 60.
60. So what do I get for a final answer on this one? Yeah, Chris?
120 degrees.
120 degrees. And that's it.
Very good.
Any other questions on that? Okay, so these are exact answers. I think we've got one or two that ask us to do a decimal. We'll practice one of each, and then that'll be the end of this section. Okay, convert to radians, round to 2 decimal places. Convert the degree to a radian. Casey, what number is going to go in the top? If we put the 180, what's the unit that we always put on the 180? Degrees. Now we have degrees times degrees, which would be like degrees squared. So we don't want to get degrees squared. We want the degrees to cancel out. Eli?
Pi.
Yeah, let's put the pi in the top. And the 180 goes in the bottom. Now degrees in the bottom will cancel degrees in the top. If you're going to type that in, there's no point in reducing it. That just gives you a chance to make another mistake. All right, so let's type it in. How do you think I should type in pi? 3.14 or the pi button? Yeah?
The pi button,
How come?
because there's more decimal places and that's 8.14.
Yeah, if we use the pi button, it's more accurate. So always use the pi button. Do not use 3.14. Divide by 180, and we get 8.73. That's radians. Do I need to put RAD? No. So that's an example of converting a degree to a radian and rounding it off. Let's do a radian to a degree, and we'll round it off just like we did the last one. Okay, again, RAD is written next to the 3, but it's invisible. So Jack, what's going to go in the top when I convert from a radian to a degree?
Degree.
Yep, and what number do we always put with degrees?
180.
180. And the number in the bottom?
Pi.
Pi. And there's nothing to cancel out. You just want to type that in the way it is. Okay. So 3 times 18 is 54. So it's 540 divided by pi. This is how you should do it. 171.89. This is how you should not do it. 540 divided by 3.14. If I'm looking for accuracy to 2 decimal places, 88 is a lot different than 97. So the correct is the top one. Don't do it that way. 171.89. And that's how you convert between degrees and radians. Any questions on that? Okay, so I want to put up, just to remind you before we finish the last part of 6.1, the problems from this part. That's the first few problems for the homework tonight. This you did last night. Okay, 323, the questions in that red box. All right, so the last thing we're going to look at in 6.1, really two things. One is a formula to find what's called the length of an arc. And the other thing we're going to look at is angular velocity. 6.2 is on unit circle trig. We're not doing that. Okay, that'll be next week. So there's really only three slides. All right, so what I want to do is I want to figure out a formula to calculate the length of an arc. Now, one thing we can use is this fact. The size of an angle and the size of an arc are directly proportional. What that means, I'll show you in a sketch. Okay, so let's say we have an angle right there. There's an arc in green. How big is that angle? Yep.
90 degrees.
That's 90 degrees. And how much of the circumference does that green arc take up? Yep.
1/4 of it.
1/4 of it. So 90 degrees takes up 1/4 of the circle when you draw the arc. All right? Now, let's double it. Here's my circle. Here's my initial side. Here's my terminal side. Here's my arc. How big is that angle this time? Yep.
180 degrees.
It's 180 degrees. How much of the arc does that angle take up? Or how much of the circle does that arc take up? Yeah, half. So notice what happened. When you doubled the size of the angle, you also doubled the size of the arc. That's called directly proportional. If you tripled the size of the angle, you would triple the size of the arc. If you made the angle half as big, you would make the arc half as big. They change together, the same rate. That's directly proportional. And when two things are directly proportional, you can set up what's called a proportion to set up an equation and solve for it. Okay? So, to set up a proportion has 4 spots in it. Top and bottom on the left, top and bottom on the right. The problem is to set up a proportion to convert between, or to figure something out, whether it's arc length or whatever you want to figure out, one side of the proportion has to be a known fact. So let's say I wanted to convert feet to inches. Can somebody give me a fact that is true about feet and inches? It can be any fact. I'd prefer a simple fact, but yep.
1 foot is 12 inches.
1 foot is 12 inches. Now, let's say I wanted to convert 8 feet to inches. All I'd have to do is put 8 feet on this side, put inches on that side, and I can cross multiply and figure out the answer. Now, she picked a 1 and a 12 because she put a 1 here and a 12 here. Does that mean I can only put 8 here? Like, could I do 9 there? Let's say, how about 12? Yeah. Just because we're starting with the fact that 1 foot equals 12 inches, these are 2 specific numbers, it doesn't limit what number you could put right there. You could put 16.5 if you wanted. You can put anything. But you had to start with a true fact on one side. We have to do the same thing here. We have to start with a true fact about arc length. And something we just went over, like 10 minutes ago, is going to help us. All right, so what I've drawn here is 2 angles called theta, theta 1. The arc created by theta, I'm calling S, and the arc created by theta 1, I'm calling S1. So here's the 4 things that you would plug into a proportion. 2 of them, though, you have to know. Just like this. You have to know a connection between 2 of them. So let's look at theta 1 and S1. There's a connection between the size of this angle and the size of that arc that we learned about. If this arc is a certain size, then this angle will automatically be a certain number. Does anybody remember what number that angle will be if that arc is the same as something else? Or let's even just take one step back. What would be a special length that that arc could be that's the same as something else in that circle? And if it is this, then that angle is automatically something. But you just want to know what could this arc length be the same as in that circle? Could be the same as the what?
What the other arc length?
It could be, and the other arc length is in the circle. Think of something else. Something else that arc length could be the same as. Yeah?
The radius.
The radius. That's very special. Okay? If that arc length is the same as the radius, then how big would this angle automatically be? This is like saying if you have 12 inches, you automatically have 1 foot. This is like the same thing. This arc is the same as the radius. That angle is automatically
1 radian.
1 radian. There's your connection that you can use to figure out anything else you want. Now you have a connection between the size of the arc and the size of the angle. So let's suppose that theta 1 was 1 radian. If it was, then that means the length of the arc is automatically equal to the radius. Let's use that fact just like we would use the 1 foot 12 inches to set up a proportion. Right? You have 4 things, they're all circled in green. That's what's going to be plugged into the proportion. You can set it up lots of different ways as long as you are consistent. So let's put theta 1 on the top, S1 on the bottom. If I put the angle on the top and the arc on the bottom, I have to do it the same way on the other side. Angle on the top, arc on the bottom. Now, this side is going to turn into this side. It's going to be where I plug in a fact I already know. So, the fact we already know from learning about degrees and radians is if that angle is 1 radian, it would automatically make the arc and the radius the same size. So fill in those 2 things where I circled on the left. All right, just separate it. So let's put 1 over r. There's your fact that's true. Again, not as simple as saying in 1 foot there's 12 inches because you're not used to this fact, but it's just as same idea. 1 radian over r equals theta over s. And I think I said it earlier, but how do you solve a proportion? What do you have to do? Yep.
The cross multiply?
You cross multiply. What's s times 1? Chris?
S.
S equals r times theta. There's your formula. S equals r times theta. That is the arc length formula. There's 3 variables. S is the arc length, r is the radius, and theta is the angle. It's important that you always put the angle in radians. This formula does not work in degrees. It has to be radians. Okay, so S equals r theta. I will always give you 2 out of 3 of those letters, and your job will be to solve for the 3rd one. All right, so let's try maybe 2 examples of that, and then we'll do the last thing. example here says find the length of the arc. And just continue the numbering from the last section. So it says we have a circle with a radius of 2, and we have an angle of pi over 4. What is that pi over 4? Is that degrees or is that radians? Yeah,
Radius.
it's radians. If it was degrees, you'd see a circle. We don't have the little circle. So, find the length of the arc. What's the formula that we just came up with for finding arc length? Francesca?
S equals R cubed, or not cubed, like big, right?
What is it?
Isn't it the, what was it called? The circle thingy? Theta.
Theta.
I keep saying beta.
Yeah, beta looks more like a B.
Oh, okay.
So S equals R theta. Now let's look at what we know. Did they give me S in the problem? What do you think, Eli?
No.
No. It says find the length of the arc. S is the arc length, so that's what we don't know. Did they give me the radius? What's the radius, Sarah? 2? Times. Did they give me the angle? Well, they had to. What's the angle here? 2?
Pi over 4.
Pi over 4. So the only thing we have to do is multiply, reduce first, and then write our answer. So the answer here is pi over 2. Now, what did we just find in that problem? They were asking me to find the what?
The arc.
What about the arc?
The length of the arc.
The length. So we have to, that is a length. So we have to go back and look at our problem and see what unit did they use to represent length in this problem. Tyler?
Inches.
Inches. So that's pi divided by 2 inches. What is that? About 1.57 inches. So that's an example where they give you the radius and they give you the angle, and they have you solve for the length of the arc. They also gave you a picture and a description. Usually you're not going to have both. Let's try one where you don't have a picture. It says, find the radius of the circle if the arc length is 3 pi and the central angle is 60 degrees. Okay. Let's just write the formula first. Someone remind me again, what is the formula? Yes.
S equals R theta.
S equals R theta. Let's go through one by one and see what they've given me. Bailey, did they give me S in this case? What does S stand for again? Arc length. So did they give me the arc length?
Yeah.
Yeah, what is it?
3 pi.
3 pi. So the arc length is 3 pi. So this time, I'm not solving for that. Okay, did they give me the radius? No, that's the question. Find the radius. So we don't know that. Did they give me the angle? Okay, but what do I have to be careful about? Yeah.
We have to convert it to radians.
You have to change that to radians. If you fill in 60, it's going to come out wrong. Has to be in radians, and that's what I wrote right there. Okay, in radians. So, how do we change 60 degrees to radians? What do I multiply by? Yep, Eli?
Pi over 180.
Pi over 180. And when you reduce that, you're going to get pi divided by 3. Okay. Now, I have a fraction next to a variable. Anybody remember what you can multiply both sides by to get the pi and the 3 on the other side at the same time? It's the same thing if you had something like this. You can multiply both sides by something that will move the 2 and the 3 at the same time. Yep, the reciprocal. So if you multiply both sides by 3 over pi, by 3 over pi, you're going to get a lot that cancels out. Pi's are gone, 3's are gone, pi's are gone. So what do I get for a radius in this one? Yep.
9 feet.
9 feet. There are 2 variables in that formula that have to be measured in length. S and R. If you're ever solving for either one of those, put a label of length on it. Just look back at your problem. Feet. Any question on that? All right, so that's how you use the arc length formula. That, and last thing. Oh, so the last thing is going to be kind of similar to converting between degrees and radians in terms of you want to cancel something out. If it's already in the top, you need to cancel it out by putting it in the bottom. So that's kind of the idea behind what we're going to do. So first of all, what angular velocity means, or angular speed, it's the speed of something spinning. You might have worked with or heard of like RPMs, those are revolutions per minute. That's the speed of something spinning in a circle. That's called angular speed, or angular velocity, same thing. Generally, our book uses radians to measure angular velocity, but there are technically 3 units that we use in this class to measure something spinning in a circle. We can use revolutions, we can use radians, or we can use degrees. Those are the 3 units of measure that measure how fast something spins on a circle. That's different than, say, like 50 miles per hour. That's measuring the speed of something moving straight. Something spinning has to be measured in radians, revolutions, or degrees. Now, let's take a look at this disk. And there's a formula that you use sometimes for regular speed, and it's called distance equals rate times time. I'm not sure if we've talked about it, but has anyone ever seen that before? Okay. So what I want to do, just do a little experiment. I want to spin that disk. Those 3 dots are glued in place, but I want to spin them all one time. Just like this. Okay, just watch the dots, watch what they're doing. Okay, they all just went around one time. If you compare how long it took the black dot in the middle, the red dot, and the black dot on the outside to all go around one time, how do the times compare for each of them to go around one time and end up back where they started? Yep.
Aren't they the same?
They're all the same. Each dot took exactly the same amount of time to do some amount of movement and end up exactly back where it started. But they all took the same amount of time. Now, which dot traveled the farthest? Yeah.
The second black dot.
Yeah, the second black dot on the outside. This one traveled the farthest in the same amount of time as everything else. So what does that mean? If something traveled farther than something else in the same amount of time, that dot must be what?
Moving faster.
must be moving faster. It's the only way you can travel more distance than someone else in the same amount of time, if you went faster. So if we try to describe the speed of these dots using this kind of idea, this is thinking about linear speed, it gets very confusing because every dot on the circle would be traveling at a different speed relative to its distance from the center. Okay? That gets confusing. But if we think about this in revolutions, think about it as an angular speed, we could say all of these dots made one revolution in 5 seconds. All of them. One revolution in 5 seconds. So it gives us a way to describe the speed of something spinning using the same number for every point along the disk. Otherwise, it starts getting confusing when we try to use linear speed. Right? So that's what angular speed does. So angular speed, I think I said that, is generally measured in radians per time unit. Time unit's not important. That can be minutes, seconds, hours. That doesn't matter. And if you compare that to linear speed, that's the speed of an object moving in a straight line. Angular, spinning in a circle. Linear, moving in a straight line. Common units you use to measure things moving in a straight line, you might use feet per second, miles per hour, kilometers per hour in other countries. And what we're going to do is convert between the two. That's going to be the goal. How do we convert between, say, an angular speed and a linear speed? I'm going to show you a much more basic conversion first. Probably something that seems way too simple, but it's good because it kind of shows the idea you have to use. All right, so let's just convert days to minutes. That's not even a speed. That's just time. Okay, that's even simpler than speed. Just time. 3 days. We're going to go 1 unit at a time. We're going to go from days down to the next smaller unit. What unit is smaller than a day that gets us closer to minutes? Yep. Hours. So I'm going to put a fraction here involving days and hours. Think of this 3 days like that. I want to cancel days out. Where would you put days in this fraction to cancel out? Yep. Bottom. Hours would go in the top. And now I need to know the conversion. How many hours in a day? Yep. How many? Yeah, 24. Okay. Now, days and days is gone. We got to go one more step. I want to convert to minutes. What's the next unit down from an hour? Yep. Minute, so we're going to get the unit we want as the final answer. I'm trying to get rid of hours and turn it into minutes. So where would hours go in this fraction? Bottom. Minutes would be in the top. How many minutes in an hour? Francesca?
60.
60 minutes in 1 hour. Hours and hours is now gone. And that's how you think about the units. You look at which one you want to cancel and put it in the opposite spot of the fraction. Let's multiply that out. Let's do 3 times 24 times 60. That's 4,320 minutes. Okay, any question on that one? All right, let's try a rate. So a rate has 2 labels. It doesn't just have a distance, it doesn't just have a time, it has both. 50 feet per second. What does that mean? 50 feet in how many seconds? Yeah.
1 second.
1 second. 50 feet in or per 1 second. So now this is two problems. You have to convert seconds to hours, and you have to convert feet to miles. Let's do feet to miles first. Even if you don't know how many feet in a mile, you should know if feet is going to go in the top or bottom. We're trying to cancel it out. Where would feet go to cancel out? Jake? Bottom. Miles would go in the top. Now we need to know, does anybody know how many feet in a mile? Yep.
5,280.
Yep. 5,280 feet in 1 mile. If you stop there, you'd have miles per second. We want miles per hour. So let's get rid of seconds. Where will seconds go to cancel out? Yep. Top. And we're going to convert that to hours. What's the conversion between seconds and hours? I'm sorry, no, we're not there yet. Seconds to minutes. If you knew how many seconds in an hour, you could do that. I don't, off the top of my head. How many seconds in a minute? 60. Now seconds is gone. Now you've got miles per minute. Where's minutes going to go to cancel out? We want to end up with hours. Francesca?
The top.
The top. Put hours in the bottom. And what's the conversion between minutes and hours? Yeah.
60 minutes.
60 minutes in an hour. Minutes and minutes. And there you go. So 3,600. That's 60 times 60 in the top. Divided by, it's all ones except the 5,280. Oh, I missed the 50. So it's 60 times 60 times 50. 60 times 60 times 50 divided by 5,280. So that's 34.09 miles per hour.
Wait, how did you on the calculator?
I did 50 times 60 times 60, and I knew 60 times 60 was 3,600. So I did 3,600 times 50, and then divided by 5,280. All right, so any question on that one? Yes?
This is more than just like a general question, but on like a text. Would we just like have to know off the top of our head how many feet are in a mile, or would that be like provided?
That one, you could put it on your reference sheet,
Okay.
but all the other conversions, like you should know seconds to minutes, feet
Yeah.
to inches, stuff like that.
Okay.
All right, last. It says a wheel with a radius of 18 inches is spinning at 1,850 revolutions per minute. What I want to basically figure out is, let's pretend like that tire was spinning on a machine, and all of a sudden it fell off the machine and it hit the ground. Assuming it doesn't fall over, what's going to happen is all of a sudden the tire is going to hit the ground, it's going to take off straight. I want to know how fast the tire would be going if it fell off the machine, hit the ground, and then took off. That's what we're figuring out. So right now, we know the speed is 1,850 revolutions per minute. 1,850 revolutions per minute. Well, they want seconds. Let's get that out of the way first. Where would minutes go to cancel out? Yep.
The top.
Okay, so put minutes in the top. Let's put seconds in the bottom. How many seconds in a minute? 60. Okay, so that's now we've got revolutions per second. We got the right time unit, but we don't have the right distance unit. We have revolutions. We want, you know what, just to make it even simpler, let's just do this in inches. It'll take one step off the problem. Okay, I want to get rid of revolutions. Where is that going to go? If I want to get rid of the label rev. Yep, it's going to go in the bottom. What's the linear measurement that they gave me in this problem? Angular measurement was revolutions. What are straight distance measured in? Yep. Inches. I need to figure out how many inches in a revolution. That's not a standard conversion. That's not like saying there's always 12 inches in a foot. That's standard. There's always 60 seconds in a minute. Inches in a revolution. Well, think about it like this. There's a revolution. How big of a revolution is that? It's a revolution that has a radius of 18 inches. How would you figure out how many inches in one revolution? It would really be the what of that circle. So pretend like this was a piece of wire, right? And you cut it right at the top. And then you laid it out flat. You could measure it that way. But think about how you could measure that distance without cutting it and laying it flat. Pretend like you can't cut it. How would you find how many inches in one revolution? A revolution is really just the what of the circle?
Circumference.
It's the circumference. So if you want to figure out how many inches or feet or whatever are in a revolution, find the circumference. The circumference is one revolution. What's my radius in this case? Yeah,
18.
18. And 2 times 18 gives me 36 pi inches. That is how many inches are in one revolution, or basically how many inches in one circumference. So there are 36 pi inches in the circumference. Now, when we multiply, you would have inches per second. And this is how you type it in. 1850 times 36 pi, that gives me the numerator, and divided by 1, 60, and 1. So just divide it by 60. That's 3,487.2 inches per second. Okay, so anytime you want to convert revolutions to something, you have to use the circumference formula. That's how you do it. All right, so as I said, the unit circle, we're not doing that. So I had problems up there before, was that second row of problems, so we'll do those. And try these 5 or so questions.
Can you put the other one back here too?
Yeah, I can put the other one back up. Everybody have this one?